Okay, now we can continue with the second one, second direct ray technology. This is called as laser transfer. So what we do, let me first show you the schematic and then go back to the previous slide. You'll see we have a laser here, and the laser is responsible actually transferring the material this time. It's not doing any sintering or melting operation, but it's simply transferring this main material. As you see, this is called as build material. This will be deposited on the substrate. So what, with the help of the energy actually exposed from this laser, the material, this is the build material, it will be deposited on the substrate. And the dimensions are not much. These are in some actually micrometers, very small. So that means you don't need to have a high power laser, very low ones, maybe around less than 0.5 watts. That will be enough to transfer your material. But obviously it depends on the type of your material you are depositing. For most of the cases, these low power lasers will be enough for your printing operation. And then we have another level of material. This is called as sacrificial transfer material. And as you see, during this transfer, it is evaporated. So it shouldn't be on the substrate or on the deposit material. After this transfer operation is over, it should be evaporated and removed from the environment. So you should consider the type of material you are using as the sacrificial material. It should be easily evaporated, cleaned. Otherwise, your resulting part will have two materials at the same time. So this is the main schematic of this operation. Let's go back to the previous slides. And we call this as sometime as an ablation, since we are removing and directly evaporating this material, some part of it, and removing the deposit material, the main material, from its, let's say, sheet, and then depositing it onto the substrate. The thing is that we have a kind of a rapid expansion during this laser, while the laser is exposed onto the material. So we have a kind of a shock on the material, and with the help of this shock, we have some cracks on two sides of the material, and then it's actually separated from the main material and deposited on the substrate. And with the help of this approach, it's quite repeatable and accuracy is high, and this accuracy depends obviously on diameter of your laser, the focusing diameter, and also other properties, the brittleness of your material. You shouldn't be using ductile materials. They should be quite brittle. Otherwise, with a shock wave, you cannot remove that portion from your main sheet of material. And obviously, since it's a printing operation, you need to control the location of your laser or the location of your material. So we need to have a control on XY plane or XZ plane. It depends on your orientation, but we need to have a proper motion control in 2 axes. And obviously, you can do this deposition on other layers, and then you need to have 3 axes. With the help of it, you can deposit complex patterns on especially formed surfaces. If you have difficult surfaces, and you can arrange your energy levels, arrange the location of your laser, and try to deposit such different materials on your formed surfaces. This is actually, we discussed any new things. Okay, so the pulsing actually is important in this deposition, since you will be opening this laser with a signal. So depending on this frequency, you will be controlling this deposition process. The pulses are highly important. These are some details. Now let's have a look at the detail. What happens while we are applying laser on the material? So what happens is that we have some actually waves transmitted onto the, let's say, material, and with the help of it, we will start some fractures on the opposing side of the material. And with the help of it, we will have this part removed from the main material, and they will be deposited on the other substrate. So the other thing is that you may remove this portion, but it may not be deposited on the substrate. So the thing is that your substrate should be compatible with the deposit material. Otherwise, it may not be sticking to this part. So we have a little temperature increase, so it may make it easier to stick to the substrate. But for the upcoming layers, if you have a second layer, it's obviously much easier since the deposit material will be the same as the previous layer. But for the first layer, you need to consider the actually relation between the substrate and the deposited material. This is a schematic of the overall printer or the direct write technology system. We have some components. So this is our material. It may be ink material or other type of material, but we prefer to use ink material. And then what is done? We obviously, we need to use a laser this time. They are using ENIAC laser. And we have a galvanometer. We have some optics here. It's focusing the laser to a specific point. So this time we have some extra degrees of freedom. This plate is moving since we need to move this glass plate. Otherwise, if your laser is always pointing to this region, we will not have any ink actually left underneath this region. That's why we need to also move this plate in XY direction. And we also have some degrees of freedom in terms of this mirror. We can rotate it and try to reflect our laser to different points on the plate. So it's up to you. You may fix this laser to a specific point, but only move glass plate or some extra freedoms. It's just up to you, since once you have more freedom, and that means we can have, let's say, more complicated shapes. You can deposit on angled surfaces, formed surfaces that will give you more freedom. And as you see, once this part is actually removed from the ink material or this layer, it is deposited on the table. And this is called as matrix assisted pulse laser evaporation direct write process. A very long name for the process, but the fundamental is very similar to other laser transfer direct write technologies. Any questions, guys? Okay, let's go on with some other issues related to laser transfer. Once again, we can have not just ink materials, we can have even metals, ceramics, polymers. But the thing is that if that's the case, then you need to increase maybe the number of pulses per second, or you need to increase the power of your laser. Otherwise, it will be quite difficult to actually remove these materials from the initial sheet of material or tape we can name. Another thing, which is actually kind of a drawback, we need to form a tape of these materials. Otherwise, you cannot have them underneath of your printer. If you look at here, we always have kind of tapes or sheet of these materials. So if you cannot form such a tape, then that means your material cannot be printed with this technology. You need to find another technology to print your material. And another issue, another drawback about this process is that you sometimes have unused portions left actually in your tape, and that will obviously be wasted. So you need to be aware of it and design your motion, let's say, system and other designs accordingly. But the advantage is that it's quite repeatable and its accuracy is higher. It depends again on the motion control systems and the focus of your lasers. Any questions, guys, about this technology? This is over. This was the second type of direct write technology. Do you have questions about it? If not, then we can jump to the third type. This is called as thermal spray direct write technology, and I would like to start with a company. It's called as Mesoscribe. Let's have a look at their, I will share you the website in a moment. Yes, this is their website, Mesoscribe Technologies, and as you see, they are printing such little kind of heaters or antennas on these mostly planar or sometimes some foam surfaces. And they are using thermal spray. Let me check their other products if they have any. Yes, here you see they can also use the same technology, direct light thermal spray technology, to have such even antennas or some other, let's go back, other wirings, even sensors, but they're always using direct light thermal spray technology. And this is an additive manufacturing technology, and we don't have much companies working in this field. For instance, you may print a kind of an even sensor on a specific surface, and their resolutions are high, so you can have these sensors in some micrometers, some millimeters level. It is a nice example of direct light technologies. So what is the fundamental of this technology, thermal spray? As the name implies, we need to heat the material, and then by using some pressure, we need to spray this material on the surface. So as written here, it accelerates the material to highest velocities and then deposit this material onto the substrate. You may have the material in powder form or wire form. It depends on your specific material you have and the type of system you have in hand. And with the help of the plume, actually, we are melting this material and then imparting it to the material. And with this, we have high velocities, high thermal and kinetic energies. You can use several materials, metals, ceramics, polymers, or even composites can be used in this technology. And the deposit material might be in solid state or in semi-solid state, but it cannot be completely in liquid state. And the advantage is that we can do this process at very small lower temperatures, maybe around room temperature. But if you are using metal and highly difficult material, maybe like steel or aluminum, you may need to increase these temperatures a little bit. So this is the fundamental of the thermal spray. So we need to have a kind of a gun. We need to apply energy to it so that the materials will be deposited at high speeds onto the substrate. But if you have a close-up view here, you will have some grainy surfaces, but not that much as in the case of other main printing systems, main additive manufacturing systems. It is a bit higher, the quality is a bit higher than, for instance, FDM or selective laser sintering. So what are the main characteristics? You can have high volumetric deposition rate, especially if you are using very big guns. If the tank is larger, then that means in the same time, we can deposit more material. And you have the flexibility of using different materials. You can play with the properties of these materials, so it has such properties, such nice properties in terms of materials. And you don't have much material, much thermal input. So if that's the case, then that means you're not actually changing the property of the substrate. But if you deposit the material at high speeds and high temperatures, then they may affect the quality of the substrate material, and these may not be the case actually you want to have in your final application. So in summary, it's a nice property of thermal spray direct light technology to deposit these materials at low temperatures. Another nice thing is that you can control the size and also the shape of this deposit materials. How you can do it? You may use such a special system. It's called as aperture system. So you have some opening. Actually, this is a gap where you can consider this one as a nozzle. You are depositing the material from this opening, and since these parts are moving, we can increase the size of this nozzle. It may be a rectangle, or it might be a little square. So it's up to the position of these, let's say, moving items. So with the help of it, you can increase the deposition rate. You can switch to a high resolution or low resolution. It's up to you. So in summary, we say that the temperatures are not high. So at low substrate temperatures, you can do the printing, and since it's done at low temperature, you don't need to do any post-processing operation. And another thing, you may have multiple layers with different materials. You may start with an insulating layer and then another conductive layer. You may have some electronic layers. You can print capacitors, resistors. They are all possible with this technology. And as we have seen on the website of the company, you can even print some sensors, some thermocouples, antennas, and some other devices. So this is actually all for the thermal spray. Yes, Murat?
Hocam 30. slayttaki sistemi tekrar anlatabilir misiniz acaba? Ben bunu kaçırdım da.
It's a very simple system actually. Although they have got the patent, I don't know how they got it. So with the help of this part, these parts are moving. Let's focus on this one. It's moving in plus y and minus y direction. Assume that this is moving in minus y direction a little bit. And then what will be the size of this opening? Let me draw it here. It will be like this, right? Since this part is moving downwards. And the advantage of it is that you can obtain any box sizes, rectangles, little squares, little rectangles. They are all possible with the help of this simple patent. But as I said, they got this patent. Although it's very simple, they got it.
Teşekkür ederim.
You're welcome. So now let's switch to another direct light technology. I think this should be the fourth one. Beam deposition, direct light technology. Not complicated. In this one, we are using actually vapor deposition. And then how do we obtain this vapor deposition? We have condensation or some chemical reactions. So we need to use these actually methods to convert the material from a vapor state. And the most fundamental thing, the most popular one is the chemical vapor deposition. We are using thermal energy to convert our gases into the solid particles. And then once you obtain these little particles, they can be deposited on different parts. And that's a very nice technology, and it's mostly utilized for actually coating the cutting tool materials, cutting tools. The tip of the, for instance, the cutting tool might be deposited with titanium carbide, and this is done with chemical vapor deposition. We have a video about this one. Let me show you chemical vapor deposition. Oops. Let me share it with you. It's describing the fundamentals of chemical vapor deposition. And we can also use this one as a writing technology. It's very simple. So you can have different materials. It might be a photoinitiator, you have monomers. Then this vacuum chamber, we will have the actually polymerization. So in this chamber, we will have polymer is formed. And then once you have the proper material formed, and they will be actually covering the surface of the part actually you have in this. Let me show it in this part. Yes. So we have the parts actually in this chamber. So once your polymers are formed in this chamber, they will be deposited on the parts you put actually in advance into this vacuum chamber. And we will be using the same principles while using the technology as a direct write system. And you can obviously do it on very complicated shapes. The geometry, the complexity of the geometry is not a concern, since we don't have a tool which is moving over it. We have just a vacuum chamber, and then the materials will be deposited on the parts you have in that chamber. And then now we have a bit different version of it. This is called as laser chemical vapor deposition type of beam deposition direct write technology. Obviously, the laser is a heat source in our case. We will be transferring this gas material into solid materials and then depositing it onto the substrate or parts we have in the chamber. So you may apply these gases by using some jets, and obviously the quality, the resolution will depend on the type of laser you are using. This beam diameter, density, and the wavelengths will affect the quality of your deposition. And with this way, you may deposit several materials like metals, ceramics, composites, and even on you can deposit materials on carbon fibers or different carbon structures. And the fundamentals are somehow similar to the microthermal spray. Again, you don't have any post-treatments. The temperatures are not high, and some specific materials can be used in this technology. And the complexity of the geometries are not as high as in the pure chemical vapor deposition, since you have a laser. This laser needs to cover the surface, so you have some limitation in terms of geometries. And you see that we have a highly complicated system. We have carbon dioxide, laser beam, some gases are actually jetted here, and we have the substrate here, and with help of the laser, this material is heated and then deposited on the substrate. And underneath we have some other controlling thing actually, since this is a table or a build plate, you can say. With the help of these underneath mechanisms, you can control the position of this table so that your laser will be actually depositing the material onto a specific point. But obviously, this is a quite complicated system, and we don't have much commercial systems. Most researchers are focusing on these technologies. And the disadvantage is that the deposition rates are not high. We have low deposition rates, and the system is quite complicated, expensive. We don't have commercial systems, and the temperature is higher in most of the cases, depending on the material. But for most materials, we need to have high temperatures to deposit the materials on these little substrates. And since the system is quite complicated, you cannot have, for instance, an available product and then deposit materials on it. You need to start with a new material. So it's not suitable for printing, let's say, sensors or antennas on available structures. Now we have another type of direct write technology. This is called as beam deposition. And underneath beam deposition, we have focused ion beam. In the previous one, we had laser beam, but the only difference is that we are using focused ion, and the rest is somehow similar. So I'm not discussing the details, but the fundamentals are the same. Again, their resolutions are high. And the advantage is that this time, since you are depositing ions, you can actually repair some electronic circuitries. But obviously, it's costly approach, a costly repairing approach. You can only do it for very expensive circuitries. And then we have electron beam version of it. Again, the fundamentals are similar. This time, instead of using laser beam or ion beam, we are using electron beam. It's the slowest one in terms of other beam type of CVDs. At the resolution is higher than the laser type of chemical vapor deposition direct light technology. And now we have another direct light technology. This is called as liquid phase direct deposition. We are obviously converting the liquid materials into solid materials in this technology. We can say that it's kind of an electrochemical liquid deposition. And we can use it, we can assume it as an actually electroplating, but this time electroplating happens in a controlled manner. If you remember the conventional electroplating, what we do, we put our actually part which is to be plated, and then we have another material, and with the help of the chemical reactions, the part is actually covered with the other material. But this time we will be doing this plating operation in a controlled manner. I think we should have a schematic here. Yes, it's here. This is a substrate, and we have a kind of an printing head. This is moving on the plate, and with the help of, again, the principles of plating, we can deposit material on the substrate, but this time in a controlled manner. So that means you can deposit very specific shapes. You're not covering the whole substrate, but you are depositing into very little, let's say, areas, and you can have such specific features. But the rest is the same as electroplating, but the difference is we have a pin which is moving in 3 axes. It's obviously a slow process. You can increase the speed of it by having some extra powders around. So with the help of it, the deposition rate might be increased. But the rest is not complicated. Any questions, guys, about this liquid phase direct deposition? And then we have another direct light technology. This is called as beam tracing. And it's a kind of an hybrid approach. We have additive and subtractive parts. So that's why we call it as a hybrid approach. And in this case, we have some layer-wise approach, layer-wise additive approach. And then with the help of the beam, we do kind of subtractive process. So for the additive part, we can have we can use coating techniques like vapor deposition, chemical deposition, or chemical vapor deposition, maybe simply electrochemical deposition. And then after you obtain this layer-wise a layer of material, then you can use some other beam technologies to remove material according to the defined paths. So what do you think, which process is similar to this one? Bond and form. There's an answer on the chat and other areas. So it's very similar to sheet lamination process. One of them, you have some sheets of material put on top of each other, and then what we were doing, if you remember, after one level, we were doing some machining. And this technology, this approach is very similar to that. We have a layer of material, and then we do some machining with the help of these beams. And you can use any beam technology, and you can use any coating technology. So if you have electron beam is used in the process, then it's called as electron beam tracing, but the rest is the same. You may further use focused ion beam, and they have some advantages. For instance, with focused ion beam, you can have gradient structures by using laser beam. You can even cure the material. So you may also use it on the additive part, but also use for subtractive part. The rest is the fundamentals are the same. So what are the main properties of these hybrid technologies? We have an actual trade-off between the material deposition speed and the accuracy. So we will be combining these additive and subtractive technologies to increase the deposition rate and also increase the accuracy. And this is only possible with hybrid approaches using additive and subtractive technologies at the same time. So in the basic form, we are depositing material and then removing these material with the help of the laser or other types of beams. So where we can use all these direct light technologies, we have covered all of them. There were 6 different types of direct light technologies. Their main properties are that we can use several types of materials. Even we can print resistors, capacitors, some sensors, batteries. They are all possible with these technologies. Even you can deposit living cells. Live cells can be deposited. And another thing, you can use various substrates. The initial material, it might be plastic, metal, even it might be a cloth. And with the help of these advantages, in summary, you can deposit, you can fabricate various sensors like antennas, thermocouples, strain gauges. They're all possible with the help of these direct light technologies. Here's an example. As you see, we have an honeybee, and this on honeybee, they have actually printed an antenna, and they have done it with the help of direct light technologies. And they use direct light thermospray technology. In this example, this blade, turbine blade, this part, turbine blade, and they have embedded some antenna inside, and this is done with the help of, again, direct light thermospray